Today, my topic is stats meets machine learning, what I learned from my machine learning certification. And first, I want to learn a bit about you guys. Oops, this worked. We all have to pick sides, right? And so I need to know how you identify. So look deep within yourself. Who are the statisticians? Everybody, if you're a stats person, give me a roof. Okay, I was not prepared for that. This could fail horribly. My machine learning people, give me a meow. Okay, that answers my next question. All my people who are just here for the coffee, give me a nee. Your horse sounds are better than mine. I did not practice this part of the talk. Okay, does anybody want to go back and give me a bark or a meow? Nope, everybody's remaining undecided. Okay, that's fine, that's fine. Who am I? My name is James Donahue. I'm originally from Nashville, Tennessee. That's the US. If you're not good at geography, that's fine. I'm not great at geography myself. I currently live in Hamburg, Germany. I'm a recovering academic. My focus was macro labor economics, and that brought a little computational economics, econometrics, all of that stuff. And I'm kind of a geek about that stuff. I get a little excited. You may notice that at some point. I'm an excitable person. And I have a brand new Amazon Web Service Machine Learning Specialist certificate. I went ahead and skipped to the specialist level because I am a nerd and go big or go home, right? But all opinions are my own. Amazon has nothing to do this. This talk is not at all about Amazon. In fact, it's more about the resources I encountered on my way there. Um, sitting there going through. Fortunately, most of it was recorded video lectures or stuff I read, so that there wasn't a teacher in front of me when I threw down my hat. That is a load of crap. No, you do not do that with. No one saw that. It was, yeah. And my opinions are possibly these are a lot of opinions, a lot of angry old man, stay off my lawn, you crazy kids, shaking my fist at a cloud, right? So I'm going to start with some of the clear wins and losses. First, we have asymptotics, which is a fancy word for what happens when we go all the way to, usually it's all the way to infinity. And so that is the question. The statisticians spend a lot of time asking what happens as our sample size goes to infinity, right? The machine learning people, how long until it converges, right? As t goes to infinity, we talking about early stopping and things like that. And the rest of you guys are sitting there like, guys, do you know how much RAM we have? Do you know how much computational stuff you're asking? Right? I see a couple people, yeah. I've dealt with those machine learning people and those Bayesians and stuff like that. And the winner here is clearly machine learning. I spent a lot of time. Do you know how many central limit theorems there are? Yeah, do you remember hearing? Oh yeah, by the Levy-Lundberg central limit theorem, which quickly they just start calling the central limit theorem. And then you get in like PhD level econometrics, and they're like, oh yeah, so if you have a martingale, we have a different central. And I stopped counting at 5. It's ridiculous, and honestly, kind of sort of useless. What about outliers? You've got these extreme values in your data set, and sometimes that may reflect excess kurtosis. So you think about the distribution, the tails of that. Sometimes those are fat, sometimes those are really fat. Think about the uniform distribution. That's fat tails, right? Sometimes, yeah, those box and whisker plots. I tried to kind of do a little. Green laser. They usually do those vertically. You have the in machine learning, we just drop all the dots, right? Just easy peasy. Data pipeline, scikit-learn, blah blah blah. You're done. And then the rest of you are thinking about outliers like Joey Chestnut. Did he really eat 7.5 kilograms of pumpkin pie in 8 minutes? Because that's the fun kind of outlier, right? You guys want to have Thanksgiving dinner with Joey Chestnut, right? Watch him eat all that in 5. No, anyway, that's my kind of outlier. Here the winner is stats. I heard a lot of machine learning people just making blanket rules every time, not thinking about the data generating process, but just saying we get rid of outliers. Punct. I even, and then this is the one that really got my eye twitching and me to throw it. You don't do that. Was I heard at least twice that you just normalize the data. You subtract the mean, you divide by the standard deviation. Therefore, all your data is centered at 0, normally distributed. That doesn't help with outliers. If you scale it, then anything above a 2 is an outlier, say, or below -2. But it, yeah, that's the one that made me really like. And then we have this interpretability thing. Did anybody here see Ferris Bueller's Day Off? Right? Do you remember the economics? It was a guy named Ben Stein, and he gave this really dry lecture. Bueller, anybody? Anybody? The Laffer curve. That's right. So that's the voice I want you to hear of the Fisherian influence is firmly based on anybody, the law of large numbers and the central limit theorem, right? If you have half a semester, my course will explain how to construct confidence intervals that are used by every major academic publication, especially those involved in the replicability crisis. What are these confidence intervals? Confidence intervals are this weird thing from Fisherian statistics and econometrics that you try to decide if the thing you got is statistically significant from 0. And it's this weird artifact from academic stuff, and it's awful and horribly badly interpretable. So we have our Bayesian machine learning people. Bayesian inference is far more intuitive. When we prepared these Monte Carlo simulations, has anybody ever waited on Monte Carlo simulations for Bayesian stuff? Yeah, my master's thesis took 3 or 4 hours to run the model and then to run the impulse response functions. It was kind of awful. And then the rest of you are sitting there like, wait, aren't y'all basing everything on the assumption of normality? And I know my Bayesian people are like, well, no. I mean, you can put any kind of functional form on your prior distribution. Yeah, but aren't you just using a Gibbs sampler and normal conjugate prior? And the winner is nobody. Actually, we really are. We could be doing a lot more in this stuff, and everybody who's doing stuff beyond the normal, beyond the Gaussian, you guys are heroes. Talk to me afterwards. I want to know more. I love that stuff. Yeah. So moving on to phase 2, what is bias anyway? And this is a huge. This actually kept me awake at night, trying to figure out how do we talk about these biases? What do we mean? Because when I talk about bias, my first thing is mathematical bias, right? I want to know, does beta hat converge to beta or not? We're going to get there, but then we're talking about bias in AI, and that's not mathematical bias. I want to figure out what that is, but let's first talk about where I'm coming from. I'm going to do this in the context of the linear regression and then try to step a little outside of that. So the first thing you learn in econometrics, linear regression is blue, the best linear unbiased estimator. And what that means is beta hat, so the parameter that we estimate, converges to beta naught, this mythical true parameter, which is really only true if you simulate the data, but then it is, and then you can prove that as the sample size goes to infinity, your beta hat will converge to your beta naught. And I did some simulations and then decided I didn't have time for those, so they will not be in this talk. But yeah, the question is, what's unbiased? So you guys may recognize this beta hat. The way we get there is x prime x inverse x prime y, and it's famous. If you don't understand that, don't worry about it. That's how we get there. That gets you to unbiased. That's a linear regression. Then we have a ridge regression. Beta hat equals x prime x plus lambda times the identity matrix inverse x prime y. And even if you don't really know what's going on in these equations, you know that if lambda is not 0, beta hat and beta hat lambda are not going to be the same thing, right? Yeah, no. And so, yeah, thanks for the thumbs up. If beta hat is unbiased and beta hat lambda is not beta hat, then it's going to be biased, right? That's it. That, for me, mathematical bias, we're done. Anything that doesn't converge to beta hat. So then why would we use ridge regression? And I know you guys are thinking about collinearity and stuff like that. What it comes down to mathematically is this idea of the bias variance trade-off. I stole this from IBM, and I don't quite love this because you have your low bias, that means it's only shifted a little bit, or your high bias where it's shifted a lot, and then your low variance where everything's clustered really well, and your high variance where it's just a mess. So high bias, high variance, no one wants that, right? Why would we choose low variance, high bias? Why would we ever, where am I? Here, be here. And this is where I don't love that. What if instead of these dots all being in the blue, what if they were all in the white? Then we have, if these are all in the white here, our high bias, low variance is going to be on average more accurate, more close to the true bullseye than these guys in the low bias, high variance quadrant. And that's why when we introduce a little bias, we get on average better answers. And that's why we use the ridge regression and so many other things there. So now I want to ask, and taking a quick example, XGBoost, a great classifier, won all the Kaggle competitions and things like that, right? Is this biased? So I stole this directly from the XGBoost documentation, and we have, let's look at tree 1. So we have tree 1 is a tiny decision tree. If age is less than 20, you get the 2 grandkids. If it's not, you get grandma, grandpa, and mom. What happens as n goes to infinity? That parameter doesn't change. There is no XGBoost isn't looking for the best decision tree for tree 1, because then they're looking at use computer daily, and then they're looking at 2,000 trees, I think is the default. You guys might know better than I do. We're just going to leave that there. It's not going to converge. I think it's biased. Well, why do we use that? Because then we weight those trees, and we get this great, really effective outcome, right? What about other biases? And so this is probably the bias variance trade-off. This is fine with me, as long as we know we're not converging to the true tree 1 split value. That's kind of my point, and that's fine. I don't care. But then we have these other biases. You guys know this plan, right? I see the smile. This is Abraham Wald, who was a Hungarian statistician and is famous for actually this analysis and the Wald test and a bunch of other stuff in statistics that you may or may not have heard of. But what I love about him is he is part of that great group of Jews who screwed over the Nazis. And that's what he did with the Allied bombers came back, and for the uninitiated, they gave Mr. Wald and others this diagram of, okay, all our planes that came back were shot somewhere with a red dot. We need to add more armor to the planes. Armor is heavy. Where do they add the armor? We think the wings and the tail. Right? No. Because we're only looking at the planes that came back. This means a plane can come back with all of these holes, but this is where the pilot lives. Wings can take a lot of bullets. Pilots, not so many. Bullets are very, very bad for pilots. And also apparently engines and apparently tail gunners. And that's what Mr. Wald said. Dr. Wald, I guess. Columbia, I think he got his PhD. Um, and I I think that is where this selection bias, survivorship bias is not all of selection bias, but so much of if it got posted to Reddit, it got put in Chat GPT. So then we have to think about who's on Reddit. It's a bunch of people that look like me, right? That's where you so the bias comes from not, these planes are not adding mathematical bias. They're adding data bias. And that's kind of my takeaway here. And I'm about to get in trouble, and so everybody, uh, do me a favor, give me your most unhappy face. Hmm. Not the bias variance trade-off. This. I'm sorry if you like it. I kind of hate this graph. Let's go through. We're talking about model complexity, and then we're talking about total error. So the idea is with a really simple model, you get a lot of error. With a really complicated model, you get a lot of error. I'm not sure. I think the idea, this is common in machine. I stole this off the IBM website. I've seen it a lot of other places, including it's on the Wikipedia page for the bias variance trade-off. Um, so I think the idea is a test set. You get a lot of error. But it never says that explicitly. So that's already. But we'll assume a test set. Let's move on. Model complexity bias. Bias is very high, or error is very high, or bias error. I don't know what this red line means because it's on the error axis. So is this bias error is very high, or bias is very high, and then you move to but wait a minute. I thought a linear regression was an unbiased estimator. Well, it is. And so I'm already, you lost me there. And then the variance, the model complexity, the high variance, low error, I don't understand it. I see they're trying to go for an overfitting, underfitting thing here. It's just not the bias variance trade-off. And I'm particularly against bias here, because we have really simple estimators that are unbiased. Um, and this is the thing that really bothered me of going into the machine learning world. I'm okay with things having different definitions. It's just I just need a little consistency, a little explainability. Um, and this is not the bias variance trade-off. If you want to talk more about this, if you want to explain this to me in a way that I've missed, let me know. I just, yeah, I hate this graph. I'm sorry. But we have a phase 3, and I have a couple minutes left. I want to draw a little line between classical statistics and machine learning. Um, and my first thought was to start at the top. And the machine learning people seem to kind of have classical machine learning and then deep learning, and I will respect that boundary. But then with your machine learning, let's talk about complicated models. And so what I did is, for this kind of, let's start as complicated as we can. I obviously cherry picked the most complicated thing I could think of from econometrics. This is my equation to scare everybody. Is everybody scared? No? Yeah, y'all ain't scared. Yeah, no, it's ARDL, autoregressive distributed lag model, and we'll start at the end. So our YT is, there's obviously some error term. We have some fixed effects. We have X from the past. So our control variables from the past, and then we have our variable of interest from the past. And then we have this seasonality thing that I've actually never used in progress, in like any kind of production research, but I left it in because it looks scary, right? Um, and my point here is, you can also look at, I did some endogenous grid searches in labor macroeconomics. At geospatial, anything gets real complicated real fast, or the fact that machine learning is really just a bunch of linear regressions and a big trench coat standing on each other's shoulders. I don't think we can get to the top and say, okay, we get so complicated it's no longer statistics, it's machine learning now. Deep learning maybe, but so then bottom up, what's the most basic machine learning model? Anybody have a suggestion? Linear regression. That's what I heard too. Simulink, maker of MATLAB. I know this is a Python conversation, but I feel like MATLAB is a. They also say like everybody gives linear regression as the first one. Does anybody have a name for linear regression? Who developed that stuff? Gauss, Carl Friedrich, right? Yeah, Jein. Jein, German for yes and no. Legendre apparently published it in 1805, and then Gauss was like, "Well, yeah, I've been doing it for 10 years." Which there's a bit of a lag in publication and who's writing everything. The foundation of the Gauss-Markov theorem, 1823. So what's the first machine that learned? That's a harder question, right? No one's shouting Bomba. The first the stepped reckoner was Leibniz 1672. That's more of an adding machine, multiplication kind of a and the first kind of publicly available calculator was around by the time Gauss got there, but not manufactured and marketed until 1851. The Bomba, which was anybody there for the cryptography talk yesterday? Yeah. If you missed it, go online and check that when the talks because he rocked it. But yeah, that didn't happen till the Enigma, World War II. This is a full century after Gauss, right? So if you want to argue that this is one of the first machines that learned, we're talking 100 years after linear regression, and they all kept on calling that machine learning. And so the outcome then for me, and take what you will, I'm just the angry old man shaking my fist at a cloud, right? If statistics is the analysis of stochastic processes, this includes machine learning. If machine learning is processes through the process through which computer models produce parameters, this includes statistics. And I'm just going to use whatever impresses people the most. So if I'm talking to somebody who wants the big mathiness, then yes, I am a learned econometrician. And if I'm talking to like an investor, yeah, so here we leverage machine learning because you never use anything, especially in cloud convert, you leverage it. So the outro, because I am officially out of time. Stats, learn, train, test, split, and benchmarking. Benchmark some stuff. Like talk about how well this stuff works. And think about being open source and for God's sake, replicable. Put your algorithm on GitHub. Machine learning, empirical foundations in Greek letters would be great. And this is the second to last version of the slides. Machine learning, find another, and everybody don't take yourself so darn seriously. This is math, it's statistics, it's the fun part of math. Enjoy it. Thank you guys. Find me on LinkedIn and enjoy the rest of the conference.